Conditional volatility is something that we also need to understand for tactical asset allocation. Let's first begin with the definition of unconditional volatility, or unconditional variance. That is simply the historical variance. We take the return history and calculate the variance, or the standard deviation is often called the volatility. It is unconditional because we are not conditioning upon the information that's available today. So if I want to forecast a volatility for tomorrow or for next month, a conditional volatility would take into account information that's available today. The unconditional volatility simply takes a past average of historical observations. It treats every observation equally in calculating that average. So in tactical asset allocation, we will use models that produce volatility that changes through time. Indeed, it's quite reasonable to assume that volatility changes through time, and most of us have experienced the volatility that changes through time. So how do we construct these models? And in this short talk, I really can't go through all of the details of how to construct conditional volatility models, but there are many possible routes. One popular route is the so-called ARCH model, or the Autoregressive Conditional Heteroscedasticity model. And the way to think about this model is with a simple example. We take, in calculating a variance, the deviation from the expected value and square it. Well, if we're working with conditioning information, then what we do is we take the returns and subtract the fitted regression returns, and that is just another way of defining the residual. So the residual, by definition, equals the returns minus the fitted values, or the expected return. For an ARCH-1 model, we would take the residuals and square them. The next thing that we do to get our conditional volatility is to run a regression of the squared residuals at time t on the lagged square residuals at time t minus 1. Now you might think immediately, well, residuals are supposedly well, they're exactly mean zero, and we shouldn't be able to forecast our residuals. And both of those statements are exactly correct. The residuals are an average zero, and via the assumptions of the regression model, we shouldn't be able to forecast our residuals if the model's well specified. But we're not talking about residuals. We're talking about the square of the residuals. And the square of the residuals is definitely not equal to zero. And it's possible that we can forecast the square of the residuals by regressing on the lag square residuals. And this is a simple ARCH-1 model. And the idea and the evidence suggests that volatility is rather persistent. So if we have a spike in volatility, it stays high for a while, and then will kind of dampen down to its long-term level. And this is exactly the sort of variation that we can pick up in these particular models. The ARCH model is a simple example of one. Indeed, it's possible to add other variables to that regression. So instead of just regressing the residual on the lag residual, we could include an implied volatility for an index option. We could include variables like swap spreads or other things that reflect confidence in the economy or in particular equities. We could use the dispersion of analyst forecasts. There's many things that we can think of doing to add to this regression model to refine the fit. There's another class of models called the Generalized Autoregressive Conditional Heteroscedasticity models, or so-called GARCH models. There's another set of models based upon stochastic volatility theory. There's a set of models based upon nonparametric density estimation. There's a whole host of models whereby we can forecast volatility, and related to this is forecasting covariance or correlation. Now, one thing I should say that is quite important in the context of asset allocation. Modeling volatility and correlation is important. And it's better to model the volatility and correlation than not to do it. However, in terms of our success as asset managers, it's much more important to get the expected returns correct. In terms of allocating the effort, in terms of the hours that you're going to put in to develop these models for a successful tactical program, most of your time should go into the forecasting models for the returns. The returns are at least an order of magnitude more important than getting the volatility and the correlations right. Let me try to phrase it another way. That you could be really way off on your forecasts of the volatility and correlation, but do just fine if your forecast of the expected return turned out to be pretty accurate. It doesn't work the other way. That you could be very accurate in your forecast of volatility and correlation, but if your expected return forecast is poor, then your performance is poor. So while it's important to model volatility and correlation, allocate your time, initially at least, heavily towards getting the expected returns forecasted in a way that is the best possible forecast that you could do.